Now let's talk about electrostatics. I want to talk about the very fundamental and basic concepts of what happens when you have what we're going to call electrostatics. Now, electro means we're talking about electricity. These are going to be positive and negative charges. So this is always going to be something charged. And statics means it's not moving. So it's not moving, so we're not talking about current, we're not talking about circuits at this point in time. We're just talking about positive charges, negative charges, and what they do to each other. Now, electrostatics is electricity at rest. Now, if you think of a couple of cases of electrostatics, you might think that it's not really at rest, but really it is. When you are standing there and you touch a Van de Graaff generator and your hair stands out, electrostatics is what causes your hair to stick out. Lightning is actually an example of electrostatics. It is, this is a current, a flow of electrons. But what causes the electricity to occur is electrostatics. Now, suppose I have a rod and some sort of dry cloth. And if I were to rub them, I would get this crackly, static feeling. These are all electricity at rest. Now, we're not worried about what happened as it zaps you, okay? It's kind of fun to play with, but we'll discuss current in the next unit. Now, electrostatic forces come from atoms. This is essential. They are not magic forces. They were not invented to harass you, not solely harass you. Suppose you have an atom and all of the protons, all of the positive charges are sitting here in the nucleus. Now, you remember, protons are positive, electrons are negative, and all of the protons are in the nucleus. I don't know if you can read that. And the electrons are orbiting. Okay, so the electrons are out here orbiting, and the electrostatic force, the attraction between the protons and the electrons, is essentially one of the stronger forces that we deal with in nature. And as a matter of fact, electrostatic forces are much stronger than gravity. Gravity is actually a very weak force, kind of a cool concept. We'll do some computations later on these. Now, Niels Bohr came up with a very basic structure of the atom. Now, if you look at this, you have protons in the nucleus. Okay, you need to know protons are in the nucleus. And protons are positive. We're going to get into this more in a bit. Neutrons are also in the nucleus. I'm not writing very well tonight. But they're neutral. They have no charge. They actually don't come into this electrostatics discussion. They're very important in chemistry. But then the electrons are spinning out here, and the electrons are negative. All right, that's not a very good E, is it? Now let's go and look at what happens. You see these two protons right here? They're terribly close together. Well, you remember positive charges repel each other. So they're actually pushing away from each other. All right? Two negative charges will also repel each other, while a positive charge and a negative charge are going to attract each other. So this proton is being attracted to this electron, and this electron is being attracted to the proton. So there are more forces. There's actually something called a strong force, which is holding our nucleus here together. But Niels Bohr came up with some fascinating ideas of how positive and negative charges make up the structure of our atoms. So when you do chemistry, remember what you're doing is really physics. Now, how do two objects get charged? Well, let's look at this sodium atom. Oops, didn't mean to do that. Let's look at this sodium atom. And you see how it has an inner shell that is full and it is stable. And then it has a second shell, which is full of 8. The inner shell is full with 2. Now you see how it has this one extra electron out here? It's not very tightly bound to the nucleus. So it is going to want to go away. All right, it's just going to want to fly off and go somewhere else. When that happens, I have 11 protons in the nucleus here, and 11 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But here, I only have 10 electrons with 11 protons. Because I have more protons than electrons, the sodium ion is positive. But we're going to learn about something called conservation of charge. This electron doesn't just go away. What does it wind up doing? Well, if we look at the chloride atom, it has 1, 2, 3, 4, 5, 6, 7 electrons in its outer shell, but it really wants 8. So it kind of steals the electron from the sodium ion. So now the chlorine atom, chloride ion, has a complete outer shell of 8 electrons. And the sodium ion has an outer shell now that has 8 electrons. It's just one shell shy of what it started with. Now, when I say negative, I just mean it has more electrons. When I say positive, I mean less electrons. We're going to learn that the electrons are what? Move. Okay, your protons don't really move much at all. The protons, remember, are bound in the nucleus. So in order for the protons to move, you have to rip off your nuclei, which kind of is like tearing up your fabric. Remember I told you there's something called conservation of charge. So if I have a balloon here that is pretty much neutral, it's got positives, it's got negatives, but it's pretty balanced, and you have hair, and you do all mostly have hair, and it's got positives and negatives. When you rub it together, like so, you find that you wind up with positively charged hair, and if I were to have shown you this balloon, the balloon would be predominantly negative charged. Now the charge didn't go away, it went from her hair to the balloon. There's my balloon. All right. If you do John voltage, which you're going to do in class, you're going to see that John is scraping charge off the carpet, and he winds up discharging it on the doorknob. And the same thing with the balloon and the sweater. We'll do those together as a lab in class. Now, there are 4 kinds of materials that you need to know about. The first one's conductors. All right, a conductor is a material that has electrons that can move freely. You see how these atoms are arranged, so the electron can move through. I mean, it's deflected a little bit, but for the most part, the electrons move very nicely. Now, good conductors are also good conductors of heat, because remember, heat is when the electrons bounce off and transfer their energy. Now, most metals are very good conductors. So a lot of times I will say metals and conductors, and I really mean really good conductors. Now, insulators are when the electrons are tightly bound, so the charge can't flow through. You see here this path it can move through, but it's got a bunch of squiggles it's got to go through. Now, insulators are not good conductors of heat. Rubber, glass, foam, plastic. These are not good conductors of electricity or heat. So a good conductor is a good conductor of heat and a good conductor of electricity for the same reasons, because it has free electrons. Semiconductors are really fascinating, and that wonderful cell phone you have sitting in your back pocket or possibly in your lap right now that you're texting somebody over would not exist without semiconductors in Silicon Valley from years ago. A semiconductor is a material that's somewhere between a conductor and an insulator. Usually it's germanium or silicon. So Silicon Valley literally got its name from the semiconductor industry. Now, what's fascinating about semiconductors is in their pure state. So when you have pure silicon, it's an insulator. But if you put in a little bit of impurity, it actually increases the ability to conduct electricity. Kind of strange. You put impurities in, and it increases its ability to conduct electricity. It's just totally fascinating, the entire science of semiconductors. And the last kind of material you need to know about are superconductors. Now, when you have a superconductor, it's usually at very low temperatures, like 2 or 3 or 4 Kelvin. So temperatures that you're not going to encounter on a daily basis. And the conductors allow the electrons to flow with no friction. With no friction, okay, you wind up with this nearly perfect conductor. Now, tin, aluminum, and some metallic alloys can be superconductors at very close to absolute zero.